Hello everyone, my name is Jing Chen. I am a PhD student at Center for Earth Observation Sciences here at University of Alberta in Canada. Also let you know that the chat will be open to any questions you might have. Today I'm here to talk something about spatial analysis, spatial modeling, especially on the applications of land use and land cover change, which is short for LUCC. First, as the main objectives, I will be talking them. I will be introducing some basic conceptions, such as spatial data, spatial analysis, and spatial modeling, to help us understand this lecture better. For spatial analysis, I will talk several common methods of spatial analysis, and then will be the applications on it. Next, I want to talk something about spatial modeling. They are how we classify the spatial models, and what the main purpose and the main process of modeling are, and what the key points are in the recent research. Finally, I want to introduce a modeling software, STELLA, including the main interface of STELLA, how it works, and a simple example of its application. So here we need to understand what differences are between spatial data and non-spatial data. Spatial data is also known as geospatial data and geographic information, as we can see from the left figure. The data or information can be defined as non-spatial data or information which is identified by the feature of geographic location. And spatial data is usually stored in two formats with specific coordinates. One is vector format, such as points, lines, and polygons. The other one is raster format. Spatial analysis is also called locational analysis. This is a type of geographic analysis which seeks to explain patterns of human behavior and its spatial expression in terms of mathematics and geometry. And it is composed of terrain analysis, spatial allocation, spatial correlation, spatial interpolation, and so on. I will introduce them later. Spatial modeling is an analytical process conducted in the conjunction with geographic information system in order to describe basic processes and properties for a given set of spatial features. It is also considered as an abstraction and simplification from the real world. One of its main purposes is used to be reproduce and simulate the dynamic process of land use and land cover change. That is also the key point of this lecture. Meanwhile, it provides the determination and evaluation to the decision makers. Then we can see the result of terrain analysis from this page. It's one of the most common used methods in spatial analysis. They are calculated from DEM data, which refers to digital elevation model showing the 3D terrain surface. The left one is slope analysis. It is showing the slope distribution of research area. The redder area represents the steeper place. On the contrary, the greener one refers to the flatter place. The slope is an important factor of topography. It's also a determinant of potential land use in the future. Slope aspect is on the right. It is derived from DEM as well. There are three aspects and flat area. It influences the local climate by absorbing the sun's rays in different directions, and it can redistribute the solar radiation, and it determines the plant growth to some extent. Next, I want to talk about spatial allocation. As we know, the non-spatial data is much easier to access than spatial data. That means most of the data has no geographic information. So how to allocate non-spatial data spatially? is a key point in this part. Basically, three spatial analysis can fulfill this allocation. They are overlay analysis, buffer analysis, and network analysis. I will introduce these three methodologies by taking population distribution as an example. Generally, we can get a total population of a district, but how it distributes spatially, we don't know. For overlay analysis, it can help us to extract implicitly spatial information by operations of clip, intersect, combine, erase, modify, and so on. It is also applied in optimal site selection or suitability modeling. I use overlay analysis to figure out the theoretical suitable area where the population was supposed to be, such as a big city, the flat area, the high density of road system area. For another cases, we also need to select a zone around a map feature measured in units of distance or time. Buffer analysis is a good tool used in such a proximity analysis. The last one is network analysis. It aims to solving complex routing problems by analyzing the connectivity and accessibility of network to gain efficiency and model operational rules. We can see the figures. The upper one shows the population distribution after spatial analysis. The darker red represents the higher population distribution area. The lower one shows the relationship between the population distribution and other related features. Then is spatial autocorrelation. It is based on Tobler's first law of geography. That is, everything is related to everything else, but near things are more related than distant things. So spatial autocorrelation is for measuring and analyzing the degree of dependency among observations in geographic space. Totally, there are three types of autocorrelation. There are positive autocorrelation, no autocorrelation, and negative autocorrelation, as the left figures show. The features in the first one are the spatially clustered in the neighborhood, so it is positive. The second one is in a random and disordered layout, so it is no autocorrelation. The last one indicates the neighboring features are more dissimilar than expected by chance, so it is negative. The commonly used indices for measuring spatial autocorrelation are Marine psi, LISA, Jerry's C, Getty's G, and join count. Sometimes we want to estimate variables at unobserved locations based on the values at observed locations. For example, we observed precipitation and temperature at meteorological stations, but the collected data cannot cover the whole research area. In this case, we can use spatial interpolation to achieve it. The left figure illustrates the estimation of accumulative precipitation in Guanacaste, a province in Costa Rica based on 18 stations data. The green means high precipitation. The other one is the estimation of the temperature in Guanacaste based on the same stations. In a similar way, the right represents the high temperature. For spatial interpolation, basic methods include inverse distance weighting and kriging. For the next part, I will talk about spatial modeling. This flowchart, as we can see, shows the fundamental steps of spatial modeling. First, we should know what problems is going to be solved. Then, using abstraction, simplification, and hypothesis to confirm variables and parameters. The third step is the variable assignment. In this process, if the variables and parameters are not supposed to be adjusted for the need of your problem, return to the last step and confirm new ones. Next, connect every part of this model and run it. The fifth step is doing examination of the model to confirm it meets your accuracy. If so, your model can operated and applied. If not, return to step 2 again until you get a model up to your standard. What is the main purpose of spatial modeling on land use and land cover change? Basically, it is devoted to solving three problems: why, where, and when. Why means why land cover changed and what caused land cover change. Where refers to where the land cover change happened. When is when it changed and how fast it changed. There are two main sorts of solving land use and land cover change problems. One is detecting land cover changes by remote sensing data, sensors, statistic data, and so on. The other one is describing the changes using some set of human and natural factors. Next, I want to introduce four models in the field of land use and land cover change. The first one is multi-agent model. It is an agent-based model. What is so-called agent means a real or abstract entity which can act on itself and its environment. Agents can communicate with each other in a multi-agent case. Like the things link people and pixels. It simulates decision-making with individual agents of land use change explicitly expressing interaction among the individuals. Nowadays, most multi-agent models can only simulate a very simplified process of land use change. In the future research, more interaction agents and factors should be taken into account to make a comprehensive model. In the early 1990s, mathematical and computational capacity limited the operation of this type of the model. In the next few years, with the improvement of mathematical and computational capacity, many researchers have developed multi-agent models to simulate changes not only in the area of land use change but also for many other purposes. At present, the biggest problem at this point is how to obtain sufficient data at an individual level and how to develop a very parameterized and validated model of decision making. Secondly, its conversion of land use and its effects model, short for CLUE model. It's a kind of dynamic simulation model using empirically derived relations between land use and driving forces from cross-sectional analysis at multi-scales. CLUE model is based on a framework which uses three scales. The national scale is for demand calculations, and the two spatially explicit scales to take driving forces at different scales into account. At the same time, this model is effectively combining biophysical drivers and human drivers to predict land use change in the future. The advantage of using a CLUE model is that it can cover a wide range of biophysical and human drivers at different temporal and spatial scales. Whereas the disadvantage of CLUE model is that it may limit the consideration of institutional and economic variables. Thirdly, I want to talk about cellular automata model. It's widely used in analyzing the spatial interactions. And there are also many applications implemented in land use models that can simulate multiple land use types. Cellular automata can calculate the state of a pixel based on its initial state, the conditions in the surrounding pixels using a set of transition rules. Although the rules are very simple, they can generate a very rich behavior. CA model and constraint CA model has its strengths. It allows each pixel to act independently according to the rules. It uses fine-scale data for detailed analysis. On the contrary, some weaknesses exist. It doesn't impact human decisions that lead to the spread of built areas. It doesn't include biophysical factors. The last one is artificial neural networks model. It's a powerful tool for land use change modeling. It uses a machine learning technique to quantify and model the complex behaviors and processes. It is used for many fields of pattern recognition, such as image analysis, land features classification, climate forecasting, remote sensing, and so on. The main objective of this model is to review and describe the changes in land use system. Changes analysis is based on the identification of the main drivers of the study area in the land use changes. The dominant transitions of artificial neural networks that can be grouped and modeled separately need to be identified. And they are called submodel. Each submodel is combined with all other submodels in the final change prediction process. Transitions are modeled using multi-layer perceptron. The following table describes some comparisons between these commonly used models. They are from the views of model types, components, what it explains, spatial interactions, and temporal scales to illustrate the differences. In the recent research, there are still three key points in spatial modeling. The most basic and primary one is scaling. Scaling expresses a process of deducing and interpreting information from one scale to another scale. It refers to land use change models transformed among different scales. Due to their scale dependency, model linearity, and complexity, these problems became tricky to be resolved. The most common series of scaling are scaling from cross-scale and from the neighboring scale. As we can see, the distinct of these two series is whether the scales included in the process of deducing and interpreting are neighboring or not. From the deducing direction point of the view, scaling can be divided into upscaling and downscaling. The first one refers to deduce and interpret information from fine scales to large scales, a process of aggregation. On the contrary, the latter one is a process of disaggregation. That means deducing and interpreting the information from large scales to fine scales. The next problem is driving forces selection. Land use change models are based on a hypothesis that humans pursue better responses of both natural and social environment to improve their economic and social cultural well-being. Thus, land use cover models are always regarded as selection functions with respect to economic and biophysical variables, which are called driving forces. As we know it, Driving forces are basic determinant in land use models. Generally, drivers are subdivided into three groups: social-economic drivers, biophysical drivers, and land management variables. The selection of driver forces is significantly dependent on the simplification made and the theoretical and behavioral assumptions used in the modeling land use change system. In a specific study, it is impossible to use all these approaches and to take every factor into account. Generally, the more complex and interdisciplinary models can lead to the more powerful results. However, the excessive drivers could decrease the explanation of models. Thus, a scientific selection rule is very important in modeling. The last problem I want to talk about is quantification technique of drivers. Actually, a lot of driving forces are qualitative variables. Although these variables can explain the state of land use pattern exactly, they are not efficient for the calculation in land use change model. Under this condition, quantification is a good choice. Summing up the previous research, three different techniques to quantify driving forces of land use change can be distinguished in generally. The first one is based on statistical theories and physical laws and uses all relationships directly on the land use processes. The second technique is quantifying drivers according to the empirical method. It relies on the statistical method and the past data to quantify the variables. The last method relies on the experiences of the experts. The core concept of this technique is that the experts use long-time experiences to make decisions and calibrations about both the weight of the qualitative variables and the transformation rules between land use at a certain location and the land use in its neighborhood. The last section, I will be talking about a professional modeling software, STELLA. STELLA is a tool to analyze the model and identify the key variables that affect the behavior of your system, and better understand its dynamics to create a system diagram that can be simulated over time, such as healthcare delivery, energy cycle, ecosystems, business systems, and transportation. It also can help us to rebuild a dynamic process in the past and forecast one in the future. It is widely used in the field of land use and land cover change, environmental sustainability, ecology, economics, demography, and so on. According to the official website, the newest version of STELLA Professional is 1.3. This figure shows the model window of STELLA. It is used to view, create, and edit your model. There are the menu bar and the toolbars at the top of the window. To select tools, execute command when you are building and modifying a model. The Properties panel is on the right to view, create, and edit properties of the object selected in the model window. The property types are under the Property panel. They are used to control various settings for the selected object. The Run toolbar is at the bottom of the window to control the execution of the model and to get an indication of the progress of a simulation. Next is the View selector, and it is used to switch between the model view and map view. From these two pictures, we can see two different views. Map view is add documentation to an object and to control its appearance. And the model view is to specify object properties like equations, arrays, scales, and ranges. Here is a simple application of STELLA. This model describes a relationship between population and natural resources. So it can be separated into two parts. There are population frame and the natural resources frame. They are connected by the ratio of the resource to person. The first part is made up by the population, birth rate, being born, death rate, dying, and the ratio between resource and person. Meanwhile, the birth rate and death rate generate dying and being born. They are two necessary elements deciding the population. Another thing may affect population is the ratio between resource and person. This ratio limits the population increasing to some extent. The second frame is composed by the natural resource regeneration rate regenerating resources consumed per person and consuming. In the same way, regeneration rate and the resources consumed per person generate the generating and consuming. Both of them decide the natural resources. Meanwhile, it is also restricted by the population. This figure shows how to set graph parameters with the property panel. You can define the start time, stop time, delta time, time units, simulation speed, parse interval, integration method, and the result of your simulation. You can also do the page settings here. These two figures show function input and graphic function input. For function input, you can build function relationships among variables using built-ins and operators. For graphic function input, you can choose the graphic types whichever you want, and edit them in detail. This figure is a summary of the variable declaration. It is including the initial states of variables, such as we set initial natural resources as 4,000, set initial population as 100. Of course, we can fix these values in another run. It is also including the function relationships among variables. They are configured as well. After the parameter settings, function configurations, and the graphic editings, we can try to run the program. The following 6 pictures shows the results from 3 different runnings. All these x-axis are the time with the unit of years. Y-axis from the top to the bottom. The pictures in the first lines are the population, being born, and dying. The second line are the regenerating, natural resources, and the consuming. There are 3 lines for each figure. This is the results of I set different initial population values. Run 1 are in blue lines with a population of 100. Run 2 are in the red lines with a population of 50 people. Run 3 are in the rose red lines, start at the population of 25. This is just a simple consideration of the dynamic process between people and the natural resources. But it explains the relationship and the dynamic changes in a brief way to help us allocate the population and the resources efficiently, to make for the sustainable development of the environmental resources. Thank you for watching my presentation and any questions.